So it's wonderful to be here. Thank you all for joining. I'm looking forward to the talk. So I'm Dan Boneh. I'm a professor of computer science at Stanford. I work on cryptography. I've been working on cryptography for a long time. I love the field. It's never boring. There's always more stuff to do, and I have to say it's an amazing area to work in. So, since this is an FHE meetup, I was trying to think about how do I combine FHE and SNARKs, which is what I've been working on recently. And so I chose a couple of topics at the intersection of FHE and SNARKs, and we'll see how it goes. The main thing I wanted to talk about is a new SNARK system called LatticeFold, which is a lattice-based SNARK folding scheme. This is joint work with Bini Chen, and if you're interested in the paper, I'll put the link to ePrint on the slide here. Okay, but since I don't know everybody's background, I know most of the folks here are focused on FHE. I thought I'd start at the beginning, and so let's just talk a little bit about what a SNARK is at a very, very high level. So SNARK stands for Succinct Non-Interactive Argument of Knowledge. That by itself doesn't really mean much. So let's just kind of explain what it is again at a high level. And fundamentally, it allows me to prove that a certain statement is true. For example, it allows me to prove that I know a message M such that the hash of M is equal to 0. And the point of a snark is that the proof has to be both short and very fast to verify. Yeah, so we call those succinct proofs. They're both short and fast to verify. Now, if you think about the trivial proof is I just send the message over to the verifier. The sending the message to the verifier is not short because the message itself could be a gigabyte long, could be very, very large, and it's not fast to verify because hashing a gigabyte of data could actually take quite a while. Yeah, it's really quite remarkable that even if the message that I have is a gigabyte long, the proof that I generate is going to be like 400 bytes, and it's going to take a few milliseconds to verify whether the message is a gigabyte, a terabyte, or a petabyte. Yeah, it's really quite remarkable that no matter how complex the statement is that we're proving, this proof is always short and it's always fast to verify. If you step back for a second and you think about the implications of this, it sounds impossible. And yet, that's exactly what SNARKs allow us to do. And of course, there's a notion of a ZK SNARK where not only is the proof short and fast to verify, it also reveals nothing about the message M. Yeah, reveals nothing about the secret witness. So just to be a bit more specific, so we understand the syntax of a SNARK. So what we often do is we encode the statement as a circuit. So here we have our circuit C. It takes as input a statement X and a witness W. And basically, this is an arithmetic circuit over some prime finite field. And our goal is to prove that the prover knows a witness W that makes the circuit evaluate to 0. Yeah, so C of XW is equal to 0. That's basically all the prover wants to do. And it turns out you can encode basically many types of computations just as circuits and proving that the circuit evaluates to 0 at the secret witness. Now, the way a snark works is it starts by pre-processing the circuit. So there's a setup algorithm that takes the circuit as input and outputs what I call the prover parameters. Sometimes this is called the prover key, and the verifier parameters, also sometimes called the verifier key. And then these parameters are given to the prover and the verifier. The prover is given the statement X and the witness W, and it produces a proof. The verifier will take the statement X and the proof and say valid or invalid. Yeah, so that's basically the syntax of the snark. And basically, succinctness means that the proof can be at most polylogarithmic in the size of the circuit. Yeah, so the circuit, again, could be huge number of gates. The proof has to be basically logarithmic or maybe log squared. And the time to verify the proof should be logarithmic in the size of the circuit. The verifier, of course, has to read the statement X. So we allow the verifier to run in linear time in the size of X, but that's about it. Yeah, so the point is it has to be logarithmic or polylogarithmic in the size of the circuit. So this is actually, snarks are actually a very, very old idea. In fact, they date back to 1991. There's a paper that actually kind of outlines exactly what snarks are used for today. Yeah, this is what, 33 years ago, where basically in the paper they say, you know, in the setup, a single reliable PC can monitor the operation of a herd of supercomputers working with unreliable software, right? So the supercomputers would generate a proof that they did the job correctly, and then the PC can very easily and quickly verify the proof is correct, and that means that the supercomputers did their job correctly. Yeah, so this is like an old idea. So why is all the excitement now? Why has this become such a big area? Well, the funny thing is when they say a single reliable PC, What they meant is a slow and expensive computer can verify the work of a fast computer. The problem that we had for 30 years is that we never had a slow and expensive computers, right? Our computers are really fast. Even our phones are supercomputers compared to what we had in the 1990s. So we never had a slow and expensive computer. It kind of took us 30 years, but we finally succeeded in building a slow and expensive computer. And that slow and expensive computer is called, yeah, it's called a blockchain. Yeah, so a blockchain is, in fact, a relatively slow computer, and it's actually costs a lot to execute instructions on a blockchain. So when it comes to running programs on a blockchain, you want to remove as much of the computation off the chain as possible. So you do the computation off chain, and then you prove to the chain that you did the computation correctly. It's exactly the vision that they had here. The only problem was there was no slow and expensive computer. And now that we have now one, all of a sudden there's enormous demand for these snarks. And I have to say, one of the reasons why it's so much fun to work in this area is unlike some other areas of cryptography, here really sort of industry is pulling the researchers. So like industry is saying, we need all these extra properties, and you researchers figure out how to do it. It's like really the cryptographers are pulled by the industry rather than cryptographers, the fancy cryptography looking for an application. So it's actually really, really kind of fun area. Of course, I love to see advanced cryptography deployed. So hopefully, more of this, the better. But of course, the point of a SNARK proof, it eliminates repeated checking of a computation. Somebody can just generate the proof, and now everybody can just verify the proof rather than redoing the computation from scratch. This is kind of the reason why it's so applicable to blockchains. And of course, ZK proofs allow us to prove facts about private committed data. For example, I might have an encrypted transaction that transfers money around. I don't want to reveal what the contents of the transaction is, but I want to prove that this is a valid transaction. So ZK snarks allow us to prove that the encrypted transaction actually does the right thing. So you can see why this is interesting in the world of blockchains. And in fact, it's so interesting that it's remarkable to me that there's a huge number of companies working in the space. This is actually a very partial map of companies working in the snark space. Some of them are building snarks, some of them are accelerating snarks, some of them are deploying snarks in applications. It's really a very active and lively community. And the interesting thing, by the way, is that there's kind of room for everybody to play. So if you're an engineer, there's a lot of room for building applications, for building tools for snarks. If you're a cryptographer, there's a lot of room for coming up with better algorithms. If you're a hardware person, there's a lot of room for building hardware to accelerate snarks. So really, this is kind of a very wide tent, and there's a lot of room for researchers of all types to kind of play here. So the first thing I wanted to do is mention like one of my favorite applications for snarks. And actually, that's one is in the area of machine learning. So an application of snarks to machine learning. And here it's a system that we built actually a year ago. It's called Fairproof. And what it does is it basically proves that an AI model satisfies some notion of fairness. So let me explain what the problem here is. So imagine you have a bank. Yeah, so in this case, I just viewed it as a large server that basically computed some sort of a model. We'll call the model theta. And the model decides whether Alice should be granted a mortgage or not based on her financial data. So what the bank will do, the model, of course, is secret because the bank doesn't want people to play with the model or to fool the model. Yeah, so it wants to keep the model secret. But what it will do is it will commit to the model, send a cryptographic commitment to the model, and send this commitment over to Alice. Now, what Alice will do is, of course, she will send her financial data over to the server, and the server will respond with a mortgage decision along with a proof pi. This is the SNARK proof. Now, what does this proof actually prove? It proves two things. First of all, it proves what we call local individual fairness. This is a notion from the algorithmic fairness community. This is a paper by Dwork and al. That introduced this notion that basically says a model is fair if it treats similar people similarly. So if our attributes are all the same, except that we have different zip codes or we have different genders, for example, this notion says the model should treat both of us the same. Yeah. And so what the proof does is it proves actually that for Alice's specific financial data, for Alice's point in the space, the model will treat everybody around that point in the same way. Yeah, so it's kind of a robustness property that says the model isn't isn't dependent on very small changes to Alice's attributes. And it also proves that the bank didn't run a specific model for Alice, but actually it ran the model that is embedded in the bank's commitment. So the same model is used for everyone. It's not that there's some differentiation between different people. Different models are used for different people. Yeah, so it's kind of neat. It's a nice application of ZK proofs that you can prove that a machine learning model is fair. But this is not what I wanted to talk about today. Uh, I wanted to talk about SNARKs and FHE. Yeah, and so I want to give two examples where SNARKs and FHE intersect. And the first one I'm going to go through very quickly. This is what's called collaborative proof generation. There's, I think, a lot of open problems here for the FHE community to work on. So let's kind of dive right in. Okay, so hopefully I'm not going too fast. Hopefully this is all clear. I wish if something I say is not clear, maybe somebody can jump and slow me down by asking a question. But I'll keep going unless I hear otherwise. Okay. So let's see. So the first area of intersection, as I said, is collaborative proof generation. And so what's the problem here? So imagine we're trying to produce a proof. The problem that we have is that our secret witness, is actually not stored on a single server, but rather the witness is shared between multiple parties. So you see here, the witness is this vector W1, W2, W3, but the vector is split across multiple parties. Now, this comes up in a lot of contexts. For example, if you're playing a multi-party game, you might imagine the state of the game is split across all the players, and together they want to prove something about the state of the game. Yeah, so that everybody's moves are consistent with one another and so on. So they can't generate the proof by themselves because they don't know individually the state of the game. The state is split, and in fact, they're not allowed to send the state of the game to each other because they want to keep their state to themselves, or their part of the state they want to keep to themselves. Yeah. So again, the question is, how do we generate a proof without actually revealing anything about the witness to the other players, other than the fact that the statement is true? Yeah. So what their goal is to actually generate a proof that this, say, a circuit evaluates to zero on the concatenated witness. It turns out, by the way, there's like interesting definitional questions here. How exactly do you define this? But once you define it, which I'm not going to talk about today, it turns out this is actually a very useful and interesting concept. It also comes up in the context of finance. For example, if you look at the financial transaction graph of the world, right? So every node in the graph is an account. No matter which bank it's an account, and an edge is basically a transfer of funds from one account to another. So every bank will only get to see their portion of this graph, right? They only get to see the portion of the graph for accounts that they manage. But together, the banks might want to get together and prove something global about the global financial graph. This would come up in the context of compliance. They want to prove to the government that the global financial graph satisfies some properties. So again, they don't want to reveal to each other what the state their local view is, and yet they need to generate a collaborative proof. Yeah, so that's again another example where you need to do proofs on shared state. Yeah, so it's a very common problem, comes up quite a lot, and so we were curious about this, and so we started studying this, I guess, back in 21, and we wrote this paper called Collaborative ZK SNARKs and how to do this. So I want to walk you through three different approaches for doing collaborative proof generation, and then we'll see which one where the open problems are. So the first option is the obvious one, which is kind of basically, let's use a trusted execution environment, right? So the trusted execution environment is going to have a secret key inside of it, this SK over here. It's going to publish a corresponding public key. Everybody just encrypts their data using the public key of the trusted execution environment. They send it to the TE. The TE decrypts, computes the proof, runs the SNARK inside of the TE, computes the proof, and outputs it, and that's it. Yeah, so very simple, nothing much to say here. This just works. And actually, there are a couple of companies that are doing collaborative proofs, basically using TEs. But we're all cryptographers. We love to see more advanced cryptography deployed in the world. So the question is there a cryptographic solution that doesn't rely on hardware assumptions, just relies on math? And so again, the first thing that comes to mind, I would call this option number two, is, well, let's use multi-party computation, right? So the way this would work is we set up some sort of a multi-party computation protocol. The parties interact among themselves in the multi-party computation. They run the SNARK prover inside of the MPC, and out comes a proof from the multi-party computation protocol. Now, this actually raises a really interesting question because now this means that we need a SNARK system where the proving algorithm is as MPC friendly as possible. If you just look at standard proving algorithms, they do a lot. There's a lot of hash functions. They're not MPC friendly at all. So the question is, can we build a SNARK prover that's MPC friendly? And that's actually what we focused on in our work on collaborative ZK SNARKs, basically building MPC friendly SNARK provers. And the remarkable thing is that in the context of SNARK proving, it turns out it's a very unusual situation, but the overhead that's normally incurred by MPC is actually quite low in the context of SNARK proving. The reason that's the case is that much of the work that goes into building a SNARK actually is linear. And linear operations can be done locally on secret shared data inside of the MPC. So for example, if you think about what a SNARK needs to do, they need to do various FFTs on large amounts of data. Well, FFT is just a linear transformation, which everybody can do on their local secret shares of the joint data. Or they need to do what are called multiscalar multiplications, MSMs. MSMs are also linear operations that can all be done linearly, locally on their secret share of the data. So what this graph shows is basically that as the size of the problem increases, the x-axis is the size of the circuit. You can see we go up to like 1,000,000 constraints. You can see basically the fact that all these lines meet means that the overhead of MPC compared to a single non-MPC prover, the overhead is relatively low. Yeah, so these three graphs correspond to three different proof systems. And again, the fact that the lines converge means the overhead of MPC is not that high. So that's kind of remarkable that we can do MPC, we can run an MPC prover, we can run a SNARK prover inside of an MPC, and the bulk of the cost is the SNARK prover. The MPC itself does not add much. Now, it turns out there was actually a lot of subsequent work on this, which is really, really cool work that shows that not only does the MPC not harm performance, in fact, the fact that you have so many servers now computing allows you to even speed things up. Yeah, and it's very clever ideas. They went into this. They use packed secret sharing to actually run the prover in MPC faster than you would run it on a single device. Yeah, again, these are the sort of things that we don't really see in the MPC world, and yet with SNARK provers, this is possible. Again, the reason it's possible is because most of the SNARK proving work is linear, is evaluating a linear function, which you can do on a linear secret sharing scheme. Now, because of this, there's actually a company that's now commercializing this. Teseo, I want to give them a shout out. Very, very cool company that basically uses MPC to compute these collaborative SNARKs. They're called co-SNARKs. It's a lot easier to say co-SNARKs. And so, yeah, so this is a company that basically allows you to build co-SNARKs on shared data. This could be like a killer application for MPC, right? So basically, MPC is used to generate proofs on shared data. And this is a very cool application for MPC. But we're not done. So with MPC, as you know, there's a lot of traffic that's involved, right? So the parties have to send a lot of data to each other. There's many rounds of communication potentially. So the question is, can we do this with fewer rounds? Can we do it with less communication? And that's where FHE comes in. Yeah. So the third option is to use thresholds FHE. And again, I'm sure many of you can see how this would work. Basically, the parties, what they would do is they would generate a threshold FHE key. So they would hold the secret key, the threshold secret key for the FHE system. The public key would become public. Now they would send the encrypted witnesses over to the server. The server would now, it's kind of interesting. The server, if you think about it, it would run the SNARK prover under the FHE. Yeah, so this, naively, this would take a pretty big server to run. You have to do all the proving computations now inside of the FHE. And so the question, and then of course, the result is an encrypted proof. The encrypted proof will be sent back to the parties. The parties would do threshold decryption to recover the final proof. Yeah, and so threshold decryption is there to make sure that they only decrypt the final proof. They don't decrypt the actual witnesses that the parties sent to the central server. And so this is kind of interesting. It's an example where we don't need verifiable FHE for this, right? The server can't cheat. If it does the wrong computation, then after decryption, we'll get an invalid proof because we verified that the proof is correct. And that's actually fast. And we don't accept it unless the proof is correct. So we don't need verifiable FHE here. The server just has to do the pure FHE, compute the result, and send it back to the parties, and they extract the proof from that. So what's the challenge? The challenge is we need now an FHE system that will efficiently support all the operations that a SNARK prover needs to do. Yeah, so this is a fantastic challenge for the FHE community. Like, let's build FHEs that are designed for, that are best suited for SNARK provers. Yeah, and by the way, it's interesting that we can push from both sides. We can try to build FHEs that are as accommodating to the SNARK provers. We can also try to build SNARK provers that are as accommodating to the FHE. So we can kind of push from both sides, and hopefully we can get something in the middle that actually will be sufficiently efficient. Now, this is kind of interesting. This is a growing area. There are already a couple of papers in this area. I pointed out to two of them here. This is from just the last year or two. What's interesting is, so what they do is basically, the first paper basically does it on what's called a SNARK based on FRI. The second one applies it to a SNARK system called Fractal. And I would imagine we'll see many other SNARK systems being FHE'd, which would be very interesting. One thing that I wanted to point out is that the second paper, I just wanted to quote the numbers that they cite that says that basically naively, if a client needs to generate a proof by itself, the paper says it would take the client 10 minutes to generate the proof. This would be on a phone or so. What they can do is they can take the client's witness, split it up into pieces, send the pieces to these parties to generate the proof collaboratively. The parties, they say, will then generate the proof in under 20 minutes. So it's a factor of two between the client and the parties generating the proof collaboratively. But the result of this is that the client computation drops to just a few seconds. So we are able to save, their claim is we're able to save quite a lot of work for the client by outsourcing proof generation using secret sharing on the witness to a collaborative proof environment. So this is pretty interesting. If this actually holds up, this is actually interesting direction to go in. So yeah, so I imagine we're going to see many more papers along those lines. It's kind of an up and coming area. So a very nice intersection between FHE and SNARK systems. So that was my first example. The second example I wanted to talk about is the main thing that I wanted to actually talk about, which is basically lattices for SNARKs. Yeah. I'm going to specifically talk about our LatticeFold system. And the reason there's an intersection here between FHE and lattices is because what's interesting to me is that exactly the same rings that are used for FHE are now being used also for SNARK generation. Yeah, now maybe I'll preempt myself a little bit and say that the reason that's exciting is because all of a sudden, all the work that the FHE community is doing on building hardware to accelerate FHE could now, in principle, be also valuable to the proving community, to the SNARK community, because we use the same rings. So whatever you guys are doing to accelerate ring operations would also be useful for accelerating SNARK generation. Yeah, so that's pretty cool, and it gives kind of a second, set of applications for the hardware that's being built for FHE. But let me step back and let's start at the beginning. So let's first of all look at pre versus post quantum secure SNARK. Yeah. And so, as we said, SNARKs basically they only have this notion called computational soundness. Yeah, they're not unconditionally sound. They're only computational sound. And this is terrible for financial application because if the assumption under which the SNARK is built, if that assumption turns out to be false, that allows the attacker to prove false statements. In the context of finance, if you can prove a false statement, that allows you to either mint money or destroy money, which is the worst possible thing that can happen. Yeah, and so we'd like to build SNARKs that are based on the strongest possible assumptions. And so we have these pre-quantum SNARKs, and I listed a few of those. Yeah, there are many pre-quantum SNARKs. And you can see that they're really quite good. They're really quite impressive. The proof size is constant. In practice, it's like 400 bytes. Verification time is constant. In practice, it's like 3 milliseconds. They're super impressive in terms of what we can do in the pre-quantum world. And the reason this is possible, by the way, is because of pairings. Yeah, so we have pairings. Pairings allow us to do these amazing SNARKs. Now, when you go to the post-quantum world, things are not as good. Yeah, so in the post-quantum world, all of a sudden you see that proof size is replaced by logarithms, in some cases even replaced by a square root of the circuit size. In practice, this translates to about 50 to 100 kilobyte proof sizes, much bigger, as you can see, than the pre-quantum size. The verifier time is also worse. It's also, polylogarithmic. Sometimes it's even square roots. Maybe just to cite one result, there's a beautiful paper. It's called Greyhound. I really like this construction. It's a lattice-based polynomial commitment scheme. Very nice paper. I really like the work. It's a very fast prover. But the only downside is if you look at the verification time, it takes about 492 milliseconds to verify one of those proofs. You compare that to 3 milliseconds, and you can see the verifier has to work much harder. And I have to say, in the world of SNARKs, having the verifier work harder is kind of a problem, especially when we run recursive SNARKs, where the verification circuit itself becomes part of a SNARK prover. Yeah, that's where we would like the verifier to be as simple as possible. Now, this is not true for all lattice-based SNARKs. There are other lattice-based SNARKs that are better, but I just like Greyhound, and so I wanted to bring out that example. Okay, so that's kind of the situation in the world of pre and post quantum SNARK. I want to kind of draw another distinction between two types of SNARKs. I like to call these monolithic versus piecemeal SNARKs. And so let me explain the differences between those two families. So what a monolithic SNARK does is it basically takes the entire statement that needs to be proved. Yeah, so the entire statement X that we want to prove, and it proves it all at once. Yeah, so this ends up with a relatively large circuit that we need to prove. When we use large circuits, we end up with very high prover memory footprints. So often these provers run out of memory. Sometimes we end up with large proofs. And in fact, the statements that we want to prove in practice are so large that we actually cannot use monolithic SNARKs. Yeah, they're just basically the memory requirements are too high, and these things are never used for very large statements. They're only used for kind of moderately large statements. The other types of SNARKs are what we call piecemeal SNARKs, and what they do. The technical name for them, by the way, is IVC or PCD, but these are not very descriptive names. So I like to call them piecemeal SNARKs because what we do is we basically take up our large statement that we try to prove and we break it up into small chunks, and then we prove each chunk separately, and then we combine those chunks. We take the proofs of the chunks and we combine those into a short proof at the very end. Yeah. So first of all, the fact that we're doing proofs now on very small chunks means that we're using very low prover memory. So this is much more practical. And what we do also is we do proofs on proofs. So we combine a bunch of proofs on chunks into a single proof, and as a result, we end up with much shorter proofs as well. So the main point that I wanted to make in this talk, and this is kind of coming, is that these lattice systems they're not so great as monolithic SNARKs, but they turn out to be great for piecemeal SNARKs. Yeah, and that's exactly where LatticeFold comes in. And so lattices really shine in this second example, and that's actually what I want to focus on for the rest of the talk. Okay, so let's talk about these piecemeal SNARKs. And so let me explain the idea. So again, this is called IVC, PCD. This dates back to Valiant's work in 2008, and the idea is the following. So imagine what we're trying to do is prove that a sequence of financial transactions are processed correctly. Yeah, so Zi minus 1 would be the current state of the system. And then a transaction comes in, and we apply some state transition function, and we end up with some new world state. Yeah, and we want to prove that this transition was done correctly. Similarly, the next transaction comes in, we apply the state transition function, and we end up with some new world state. And we want to prove that that transition was done correctly. Yeah, so the piecemeal aspect of it is we're going to prove that each transaction was processed correctly on its own. We're not taking like billions of transactions and proving that all of them were done correctly at once. We're proving that each transaction was processed correctly on its own. The way we do that is basically we augment the statement that we're proving by basically making the statement take another input, another parameter as input. In particular, it's going to take this parameter called pi I minus 1, which proves that all the transactions up to this point were processed correctly. And then as part of our statement, we're going to verify that the proof pi I minus 1 is correct. And we're going to take zi minus 1 and zi as inputs. We're going to verify that the state transition on zi minus 1 was done correctly. And we're going to generate a proof that A, we had a proof that the first I minus 2 steps are correct, and that that transaction I minus 1 was processed correctly. So you see this pi I proof basically proves that all the transitions up to this point were done correctly. And then we're going to iterate that over and over again, right? So this proof will go into the next statement. We'll verify that the proof is correct and that the current transaction was handled correctly. And then we'll produce a proof that all steps up until this point were processed correctly. So this is sometimes called a recursive snark. As I said, I like to call this a piecemeal snark because we're proving a very large statement, but we're proving it one step at a time by verifying the proof up until this point, and then extending that proof with a new transaction. Okay, so this is great. So first of all, because we're only processing one transaction at a time, we have a small memory footprint. The nice thing about this also is is you can start proving before you know all the transactions. Yeah, in a monolithic snark, you would have to collect all 1,000 transactions before you start proving the statement. Here, you can start proving as transactions come in, and you don't have to wait until you have all of them as a batch. And it turns out also you can parallelize this as a tree. We have a recent paper called Mangrove that shows how to do all this very efficiently in a tree, but I won't say any more about that. The problem with this is, first of all, the SNARK verification circuit is actually quite large. Yeah, so we're adding a lot of overhead to the statement that we're proving by insisting that we verify a SNARK as part of this predicate. Yeah, so now our box actually became a lot bigger. In fact, the sizes here are not proportional. Verifying a transaction should be a really small box, and verifying the SNARK, snark.v, is a really huge box. And the other problem is the prover now has to generate a new proof at every step of the computation. Yeah, so the entire SNARK prover has to run at every step, and that's expensive as well. Yeah, so the question is, do we have a better way to compose schemes, to compose these steps? And it turns out that's exactly where folding schemes come up. So folding is a beautiful, beautiful idea. It's due to these two recent papers. And what they show is basically that there's a way to compose, there's a way to compose proofs, or rather to compose statements very, very, very quickly. So the thing that makes this possible is what's called a linearly homomorphic commitment. So just to remind you, so we're all on the same page, we can commit to a very long vector using a short commitment. Yeah, so I'll denote the commitment by CW. And the scheme is said to be homomorphic if basically if I give you the commitment to two vectors, if you multiply those commitments, then you end up with a commitment to the sum of the two vectors. Yeah, that's a linearly homomorphic commitment. Now, let me just mention that in fact, everything I'm going to show you here is going to depend on linearly homomorphic commitments, but I will say that there's, again, really, really interesting work. There's a recent paper called ARC that actually builds folding schemes from hash-based commitments. So these are not linearly homomorphic commitments. There's a lot more complexity in doing that, but that actually is possible. And it's a very nice paper. It's a paper by Benedict, Partouche, Wilson, and William. So it is possible to do things without linearly homomorphic commitments, but I'm going to focus on the linearly homomorphic commitment version. Okay, so how do folding schemes work, and what are they in a bit more detail? So what folding schemes will do is they will take multiple NP statements and compress it into a single NP statement. Okay, so we start off by augmenting our NP statements in the following way. So to the statement, to the public statement, we already always have X in the statement. We're going to add a commitment to the witness into the statement. And what the augmented NP statement does is basically verifies that X and W satisfy the relation, but it also checks that CW is in fact a commitment to the witness. Yeah, so it's very important that the verifier is given a commitment to the witness. Now, what does a folding scheme do? What it does is, let's see, what the folding prover does is it takes, the instance witness pair that it takes two instance witness pairs, and it produces one folded instant witness pair along with the proof that it did this correctly. Okay, so that's all the prover does. You notice it doesn't actually generate a proof that the statements are correct. All it does is it takes two statements and compresses them into one and generates a very simple proof that the compression was done correctly. The verifier, what it would do is it would take the original statements, U1 and U2. It would take the folded statement U tilde along with the proof, and it would verify that the prover did the folding correctly. Okay, so again, we're taking two instance witness statements, we're compressing them into one, and then we're proving to the verifier that we folded those two statements correctly. So what are the properties of these folding schemes? Well, first of all, of course, they have to be complete. So if the folding prover ran correctly, the folding verifier should accept. And then they have to satisfy this new property. This is, again, a really interesting property called reduction of knowledge. And informally, what a reduction of knowledge says is that if, in fact, the folded instance, U tilde, W tilde, is in the relation, and in fact the folding verifier accepted the proof, that means that the prover actually knows witnesses for the original instances. Yeah, so the reason we call it a reduction of knowledge is because we reduced knowledge of the original witnesses, of two original witnesses, into knowledge of one witness for the folded statement, for U tilde. Okay, so this generalizes the notion of a proof of knowledge. You can think of a proof of knowledge as reducing witness instance witness pair a value. Sorry, you can think of a regular proof of knowledge as reducing an instance witness pair, yeah, into a instance witness for the trivial relation. The trivial relation being the one that's always true. Yeah, and so this generalizes the notion of a proof of knowledge. It's a very elegant definition, and it turns out to be exactly what's needed for folding. Yeah, so we reduce knowledge of two witnesses into knowledge of a single witness for the folded instance. Okay, why is this interesting? The reason this is interesting is because, first of all, the folding prover is much, much faster than the SNARK prover. And the folding verifier also is much, much faster than a SNARK verifier. Yeah, this is why this is so interesting. Okay, so let me explain how we build a SNARK from these folding schemes. You can probably imagine how this is going to work. What will happen is that the statements that we're folding is basically what we call an accumulated statement. Yeah, so ui minus 1 tilde and wi minus 1 tilde. These are accumulated statements of everything that has come before. Ui minus 1 is the current statement that we're proving. And what the folding prover will do is it will basically fold the current statement, the current transaction, into the accumulator, and it will construct, by doing that, it will construct an updated accumulator statement. Yeah, so ui tilde is a compression, a folding of everything that came before plus the new transaction. In particular, the statement that we're proving is basically, this transaction is valid. That's what this F is doing. Transaction was processed correctly, along with the fact that the folding actually was done correctly. So the prover is basically proving that folding up until this point was done correctly, and it basically folds those two statements into one. Yeah, and then we basically iterate this over and over again. So for the next transaction, again, we have an updated accumulator. We have a new statement that we're trying to prove, and we fold the new statement into the updated accumulator to get the new accumulator, and so on and so on and so forth, until you see at the very, very end, what comes out is actually a folded statement that folded all n transactions that we were trying to handle. But now it's just a single folded statement, and we can prove that however we want. We can use a monolithic SNARK to now prove that single folded statement. That single folded statement is only as complicated as proving a single transaction. Okay, that's the idea. Yeah, so if we want to prove 1,000 transactions, what we do is we'll fold those transactions one at a time into a single folded statement. That single folded statement is going to be a nonsensical statement, but it encodes all the 1,000 transactions. And then we would use a monolithic SNARK to just prove that final statement that comes out at the end. And that step is very fast because it's just being applied to a very simple circuit. So that's the idea of folding. And by the way, I should say folding doesn't have to be done in a line. Folding could also be done in a tree. So you can get parallelism out of this and all the good things you can imagine. So basically the world is slowly moving to these folding mechanisms, and that's probably where things will go. Okay, but so far we kind of ignored one important question, which is which homomorphic commitment are we going to use? Okay, so traditionally in folding systems, the homomorphic commitment that's being used is a Pedersen commitment. Yeah, so here I wrote down what the Pedersen commitment is. You guys are all familiar with it. Basically, this will give us a point. So let's see, we're folding elements in a finite field. So the exponents belong to a finite field of size p. The fold, the commitment is going to be an elliptic curve point, so it's going to live in some field FQ. It's going to be a pair of values over the field FQ, and that's going to be the actual commitment. And we know that this commitment scheme is linearly homomorphic. So the nice thing about this gives a very clean proof of folding. It turns out you just need to rewind the folding prover 3 times and you can extract witnesses. It's all very clean and very simple. It's kind of a very elegant construction. The problem is that there are a lot of difficulties with Pedersen commitments. First of all, Pedersen commitments require these group exponentiations over a large field. So the folding operation, even though it's much faster than running a SNARK prover, the folding operation is still quite expensive. Yeah, it requires these operations over large fields. Second of all, the folding verifier has to deal both with elements in the finite field, FP, and elements in FQ. So it has to do both G operations and FP field operations. So the folding verifier has to do operations in 2 fields, both in FP and in FQ. Unfortunately, our circuits can only operate over one field, either FP or FQ, which means that we have to do field emulation where we emulate one field using the other field, and field emulation is, again, quite expensive. Yeah, implementing one field using another field, this comes up in FHE as well, is not cheap. And finally, of course, Pedersen is not post-quantum. It's not binding. So again, the resulting SNARK would not be sound in a post-quantum world. Okay. So what we were wondering about is, can we fold using a homomorphic commitment from lattices? Yeah, and it turns out the answer is yes. This is our system called LatticeFold. But it turns out lattices, like everything, introduces a lot of complications. So let me explain what the issues are. So first of all, I would say there are lots of benefits to using LatticeFold. So first of all, to using a lattice-based homomorphic commitment scheme. First of all, we get to work over small fields. And it turns out that actually the itai hash that we end up using is actually much faster than Pedersen. Yeah, it's about 30x faster than Pedersen. As I said before, we could potentially accelerate it using the hardware that's being built for FHE. So this is another application for the FHE acceleration hardware. Maybe we can do lattice folding much, much faster as a result. And the other interesting thing is, as you'll see in a minute, using the itai hash, we only need to use one field. That is the committed plaintext and the commitment string. They both lie in the same field, so we don't have to do any field emulation, which again simplifies things quite a bit. And of course, it's post-quantum. So those are the benefits of using lattices. Unfortunately, as we said, there are lots of complications to using lattices. And right now, it's not actually clear if the extra work that's needed to make LatticeFold work is better or worse than the 30x speed up that we get from itai. That remains to be seen from an implementation. Okay, so let me explain how this works. I guess I have to start by explaining how itai commitments work. So again, I imagine many of you know this, so I'll go through this very quickly. So we fix our prime, we fix a norm bound, I call it beta, and we fix a particular dimension. And the way we commit to a vector W, the vector W has to be a low norm vector. The way we commit is just by doing a matrix vector product. Yeah, so A times W gives us the commitment CW. The vector is of dimension n, and the commitment is of dimension lambda, where lambda is much, much smaller than n. So this is the compressing commitment. The problem, of course, is that this is binding only when the vector W, when the vectors we're committing to are low norm. And this is going to cause a huge problem for us when we do folding, as you'll see in just a minute. This is simply not binding if we try to commit to large norm vectors. Now, of course, matrix vector products are linearly homomorphic, so that's trivially linearly homomorphic. But the problem with this particular construction is it's still not as fast as we'd like. In particular, to compute the matrix vector product takes lambda n operations in ZQ, right? This is basically the time to compute the matrix vector product for a matrix of dimension lambda by n. So can we do better? And the answer is yes, we can do better. And again, you guys are very familiar with this. The way we do better is we use rings or modules. So here we're going to move to our favorite ring, RQ, which is a particular cyclotomic. Uh, Now our vectors, instead of committing to vectors of integers, what we'll do is we'll commit to ring elements, to a vector of ring elements. What that allows us to do is it allows us to shrink the dimension of the matrix by a factor of d in every direction. Yeah, so the matrix now becomes only lambda times n over d squared ring elements. Yeah, and now the matrix vector product is really lambda over lambda times n over d squared ring operations. Here you can see it right over here, lambda n over d squared ring operations. And ring operations can be done almost in linear time using FFT. Yeah, so basically this gives us kind of a factor of d speed up over the basic itai. Yeah, so this is why we like to work with rings and modules. So that's actually what we end up using in LatticeFold. Okay, now again, we have the same problem that this commitment scheme is only binding when the vector we're committing to is low norm. In particular, the coefficients of W hat as elements in the ring, they have to be low norm elements. All right, so now that we understand that, let's think about what does it take to do folding using itai. And here, I'm going to only explain this at a very high level. There's a lot of details to go into. I think I'm going to need like 5 more minutes to go through this, and then we'll stop for questions. Yeah, okay, so how do we fold in general? And in particular, how do we fold with itai? Well, what we do is, remember, again, we have a commitment to a witness, and we have the witness. Yeah, and we also have the statements U1 and U2. The way we fold is basically we're going to choose a random element in our field, and we're just going to do linear combinations. Yeah, folding is literally the basic steps of folding is just computing linear combinations. Okay, that's all nice and fine. This works really well with Pedersen commitments. The problem with itai commitments is all of a sudden you just exhausted your norm bound. Yeah, so multiplying by gamma increases the norm of the witness, and the result W hat will not be, W tilde will not be low norm anymore. So this just doesn't work. We can't do that. So what do we do instead? So the question is, how do we fold while preserving the norm bound? And what we do here is actually something that comes up again in FHE quite a bit. So this is using FHE techniques in the context of SNARKs. What we'll do is actually, before we fold, we're going to take our witness. Yeah, so here we have a is an element of the witness, and we're going to break it up into chunks, into smaller chunks. In particular, we're going to write this little a, we're going to write it base b, where b is much smaller than the bound beta. For example, let's say that b is square root of beta, in which case we're going to take our witness, our two witnesses, we're going to split the two witnesses, W1 and W2, we're going to split each one of them into two chunks. So now we end up with 4 witnesses, yeah, 4 witnesses. And the folding is now, we get a more complicated relation because now the relation is going to act on 4 witnesses rather than 2. And the folding is going to be a 4-way folding rather than a 2-way folding. So we folding by choosing low norm gamma 1, gamma 2, gamma 3, gamma 4. They still come from a sampling set, but we're going to take some sort of a low norm linear combination of those witnesses. And because we shrunk the norm of the witness, when we take a linear combination, a low norm linear combination, it turns out that we preserve the norm of the resulting folded witness. Yeah, so this basically, so if you notice the way this works is we started from a norm beta element, we broke it up into lower norm elements, we folded those all together, and now we end up with another norm beta element, which is what we wanted. All right, so that's the first challenge we have to overcome. Basically, how do we fold without exhausting the norm bound? Okay, again, I'm way oversimplifying. Things, of course, are much more complicated. You can look at the paper to see how these things actually work. Unfortunately, I wish that was it. There's yet another challenge. And again, this is a challenge that comes up often in the world of zero knowledge, of lattice-based zero knowledge, which is how does the extractor work? So if you remember, for knowledge soundness, what we're supposed to do is when the folding verifier will give us the folded statement, the prover the folding prover will give us a witness for the folded statement. Yeah, it will give us some malicious witness for the folded statement, and all we know is that the folded prover gave us a valid statement, a valid witness for the folded statement. Yeah, so here it gave us a W star that actually is a valid witness. Our challenge is to extract witnesses for the original commitments. Right, so remember, this is a reduction of knowledge. So given a valid witness for the folded statement, we have to produce valid witnesses for the input statements. And so we have to produce, basically, we have to extract witnesses from these commitments. So how do we do that? Well, we do that in the normal way by rewinding, right? So we're going to rewind the prover a couple of times. We're going to get multiple, we're going to give it different gammas every time. As a result, it's going to give us different folded witnesses every time. And now to recover, again, these are linear combinations. So to recover the original witnesses, W1 and W2, from these linear combinations, we just solve a linear system. And that requires dividing by gamma 1 minus gamma 2 inverse. So we can make sure that gamma 1 minus gamma 2 is invertible. That's fine. That's not a problem. The problem is that the inverse is going to be high norm. As a result, we'll end up with witnesses, the original witnesses will be too high norm. All right, so extraction just doesn't work because we end up with witnesses that are too big. So what do we do? So this is actually, unfortunately, a bigger challenge than the first challenge. So the way we solve that in LatticeFold is actually we require the folding prover to provide range proof actually on the original witnesses. Yeah, just to prove that the original witnesses are low norm. The way we build this range proof, this is a new range proof. We build this range proof using the sum check protocol. And I'll get to this in just a second. There's a reason why we use sum check for this range proof. But basically, once we have this range proof, then we can guarantee that the extractor will always extract low norm witnesses. This, of course, takes a proof, but that's all in the paper. Okay, so those are kind of the two challenges we had to deal with. I'll say that we have some upcoming work where we even improve this solution even more. So LatticeFold is only going to get better if you wait a bit. But basically, this is kind of what I wanted to tell you about today. So LatticeFold basically is a lattice folding scheme using the itai hash as its commitment scheme. It uses small fields. It has a very efficient verifier circuit. It's post-quantum secure. And it can handle actually very large, what are called CCS, high degree constraint systems. And the reason we needed to use sum check for the range proof is because we can use a single sum check to both verify that the transaction was processed correctly and that the range proof is satisfied. Yeah, so the range proof is in some sense very cheap because it's combined with the proof that the statement you're trying to prove is already correct. So yeah, so if you take one thing away from this talk is just this fact here, that lattices, maybe they're not that great for these monolithic SNARKs, but they're fantastic for folding schemes. Yeah, and they're so good for folding schemes because the itai hash is so fast, and we can make itai hash work in folding. And as a result, we're probably going to see a lot more folding schemes built from lattices. So it's probably a lot more to do here. And yeah, so I'm at time, and so I'll stop here. And yeah, I hope you enjoyed it. Thank you for coming, and I'm very happy to take any questions. So thank you all.